All right. Yeah. Yeah. You're gonna sit down. And then, so our last lecture in today, presented by actually it's a kind of continuous talk from the last talk on Tuesday last week. Then he's gonna talk about the modeling of the solar near field.
Okay, so in the last lecture, we were talking about magnetic reconnection, how it happens in plasma. And this is a slightly different topic. You have seen in the last talk about gamma ray bulb. Now we are coming back to mostly on the sun. But whatever we are discussing over here is equally relevant for other stars as well. So the idea of saying that we want to model the solar magnetic field is that you have a three-dimensional magnetic field of the sun. But when we are trying to measure the magnetic field, mostly in the sun's case, you can measure the magnetic field on photosphere because photospheric magnetic field is stronger, typically of the order of thousands of Gauss when you are looking at sunspots. And therefore, those signals are stronger and you can measure them nicely to get the magnetic field there. But if you move higher in the solar atmosphere like chromosphere and polar corona, there the magnetic field strength is weak. And along with that, temperature also increases in the solar corona. So your magnetic field strength is also weak and temperature causes a broadening of spectral line. And therefore, you cannot effectively measure the magnetic field in the solar corona or chromosphere. So what we have available from measurement is the photospheric magnetic field. And the objective is to construct the magnetic field in the chromosphere and solar corona. So that is where this modeling of solar magnetic field comes into picture. And this magnetic field, this modeling of the magnetic field is what we call as magnetic field extrapolation. So how we do that is the following. In the current literature, there are primarily two types of models for extrapolation or modeling the solar magnetic field. One category is called the force-free modeling and another category is called non-force-free modeling. So the meaning of force-free is that the Lorentz force is zero. How we reach to that point where we are saying that Lorentz force of applicable on the plasma system is zero, that we will see in this slide. And then how we use that condition of zero Lorentz force to get the magnetic field in the solar atmosphere. So the starting of this talk is going to be this particular equation, which is shown in pink. So essentially, this is Newton's law. On the left hand side, you have mass density and acceleration term. And on the right hand side, you have a couple of forcing terms. So the first term that you have is gradient in the pressure. So this pressure is essentially your hydrostatic pressure. Here we are not talking anything about the magnetic field. So like you have an ordinary gas or fluid where you have your standard pressure, force per unit area. This is exactly that kind of pressure. And the gradient in that pressure will correspond to a force so that plasma from a higher pressure region would want to go to a region of lower hydrostatic pressure. The second term is Lorentz force. So here the current is replaced by its form curl of B divided by mu naught. And this J cross B is what we call as Lorentz force. So this force is magnetic in nature where you involve magnetic field. So the first forcing term does not have any magnetic field involved. The second term has magnetic field involved. And the third term is just the gravitational force in this equation. There are other equations of MHD also, but these are not relevant for the current discussion. So I'm going to skip that. So one important point that you will notice here is that we are talking about magnetic force, but we are not talking about any electric force in the solar atmosphere. And the reason is what we discussed in the previous talk, that when you are looking at large length scales in the system, then plasma is quasi-neutral, and effectively you do not have a lot of charge imbalance in the system, and therefore you do not have large scale electric fields, and that is why you do not have electric forces also. And another point that I mentioned is already that, okay, it is hydrostatic pressure, and it is also called thermal pressure or kinetic pressure, because like in an ordinary gas, if you put it in a wall chamber, then where is that pressure coming from? This pressure is coming from its internal energy. When you are trying to heat the gas, the particles will move faster, and then they are going to collide with the walls of the container and exert some force on that, and therefore correspond to that pressure. So that pressure is coming from the internal energy or kinetic energy of the molecules. So that is also something to know. And then last is that on the left hand side, we have dV over dt. So this is basically your total derivative, or what we call as Lagrangian derivative. So this is del by del t, that is partial derivative of velocity, plus v dot del v term, which is shown over here. So now, from this equation, we open up the total derivative and we have this kind of form. So now here comes an important approximation when we talk about force-free modeling, that the left-hand side is 0. Why the left-hand side is 0 is important to understand. So typically, the large-scale structures in the solar atmosphere, whether we are talking about large-scale magnetic loops, so these loops typically evolve very slowly. What it means is that their velocity is much less than different characteristic speeds of the system, of the plasma system that you can characterize. And I will explain more on it. Yeah, so just to see how it comes, how we can compare the velocity of those structures with different characteristic speeds of the system. So what we can do is take order of magnitude estimate. So on the left hand side, we have rho dV by dt. So if we take the magnitude of rho dV by dt and take the magnitude of grad p, so then dV by dt is essentially velocity over time, and grad p is essentially pressure upon length scale. So length goes in the numerator, and then you can combine length and t to get a velocity term. So you have rho v square divided by pressure, and then you can take that density to the denominator, so that you get pressure divided by density. And then this is essentially sound speed squared without the adiabatic index. So what you get is, by comparing these two terms, is v square over cs square, and cs square is the characteristic sound speed of your plasma system. Similarly, if you take the second term, if you take order of magnitude analysis over here, so you get rho velocity divided by time, and j is curl of v divided by mu naught. So mu naught goes in the numerator, the length scale from gradient goes in the numerator, and then you have curl of v, so you get v square. So you again combine length and time to get rho v square, and you have v squared divided by mu naught. So you can bring mu naught in the denominator, and similarly you can bring density also in the denominator, which is essentially the formula for Alfvén speed. So Alfvén speed tells you what is the speed at which magnetic disturbances are propagating in your plasma system. And lastly, if you take the term rho dV by dt with the last term rho g, so again the density cancels out. So you have velocity over time into g, and then you can use like the most basic equation from school, which is s equals to ut plus half gt square, to get a term like square root 2lg, which is the free fall speed on the sun. D would be here gravitational acceleration corresponding to the sun's mass. So you can see that by comparing these order of magnitude terms, you can get its comparison relative to characteristic speeds. And when we say that these structures are evolving very slowly, what we mean is that their velocity is much less than sound speed, alpha speed, and this free-fall speed. Alpha speed in the solar corona is typically thousands of kilometers per second. And if you calculate sound speed and the free-fall speed, these are also of the order of few hundred kilometers per second. So the speed at which magnetic structures are evolving is typically at the speed at which photosphere is driving them. That speed is mostly of the order of 1 to 2 kilometers per second. So 1 to 2 kilometers per second compared to few hundred or thousand kilometers per second is very small. And that is why the velocity term is very small. And not just that the velocity term is very small, the rate at which that velocity is changing is also very small, because there is no sudden force which can cause a large scale acceleration and therefore change the velocity, except in the case of reconnection event. So in this scenario, we are not talking about reconnection at all. We are talking about large scale magnetic structures which are moving slowly in the solar atmosphere. So then what we can do is neglect the left hand side term, and then we can arrive at this equation, which is saying that the total sum of all these three forces is equal to 0. What it means is that you have a force-free condition, that although there are different forces acting on the system, but their net outcome is 0. So then again, now follows the second step in this analysis. Now we want to compare the relative magnitude of all these forcing terms in this particular equation, that whether J cross B force is the dominant term, or pressure gradient is the dominant force, or gravitational force is the dominant term. So for that, what we do is make this equation dimensionless. We do that by setting. So here this pressure is a dimensional quantity, and then we are writing it as P tilde into P naught. So P naught is a pressure quantity, but P tilde is a dimensionless quantity. Similarly, you can write it for position vector R, current density, magnetic field density, and gravitational acceleration. So if you plug in all these things into this equation, then you get an equation of this form, where you have all these quantities P naught, L, J naught, B naught, and all these other quantities. So now here comes the important step. There is a quantity called plasma beta. So last time we defined magnetic Reynolds number as a quantity which can characterize your plasma. So another very important quantity which we use is called plasma beta. It is defined as the ratio of thermal pressure to magnetic pressure. So your thermal pressure is just P naught, and your magnetic pressure is P naught square upon 2 mu naught. So here your J naught is curl of B over mu naught. So curl will give you a inverse factor of 1 over L. So length cancels out, and then you get a B naught square upon mu naught. So B naught square upon mu naught, and then you multiply it by 2, so that you get a beta by 2 factor in this term. And J cross B term does not have any factor. And here you again get plasma beta, be reorganizing the term. You have length scale as well from the J naught. And then there is another quantity H, which is called hydrostatic scale height. This represents the height over which your pressure decreases by a factor of E. So this is given by this combination P naught over rho naught divided by P naught. So the entire purpose of doing this analysis is to check that for which particular term we have the maximum value. So here we have beta by 2, here we have 1, and here we have beta by 2 L divided by hydrostatic scale height. Now we need to know these numbers corresponding to beta, hydrostatic scale height, and so on, to see that which term is more dominant. So in solar corona, what you can do is, that is probably the simplest case. So in solar corona, you can find the values of density, temperature, and magnetic field strength. You can plug in those values to calculate beta very easily. And hydrostatic scale height also you can get from pressure, density, and these values. So it will turn out, if you calculate this quantity, that in solar corona beta is much less than 1. And hydrostatic scale height is also of the order of 100 megameters. And if you put in this number that beta is much less than 1, typical length scale in the solar corona you can take as 10 megameter for 1 megameter. And then H you can put the value of hydrostatic scale height. So it will turn out, because this term is much less than 1. So then you are getting, this entire number is much less than 1. Here we have 1, and this term is also much less than 1. So then, in comparison to Lorentz force, we can neglect the force due to pressure gradient and due to the gravitational force. So effectively, what we end up with is J cross B equal to 0. So we started with a force-free condition where the sum of all these terms is 0. And then by comparing the magnitude of these terms, the first term and third term relative to the second one, we get a condition that Lorentz force is 0 in the solar corona.
I have a question.
Yes.
In that slide. Are these assumptions on the left are valid for active regions as well?
Which assumption?
This assumption on the left side is that B square by CS square is much smaller.
Yes.
Yeah.
This assumption I would say is generally valid for if you are characterizing the system on large scale, the entire sun, then it's definitely valid. In active regions also, it is not that the magnetic field goes sudden change all the time. It will first accumulate some stress, that is, it will store energy over a large period of time. And then suddenly it goes out of equilibrium to cause reconnection and a flare or any other activity. So during those times, yeah, this assumption can be taken.
But velocity is, I think, much larger in active region.
What there are number that you are thinking? What
Yeah,
is the
30 kilometer per second.
How much?
30, 50, 30 to 50.
30-50 kilometer per second would also typically come when you have reconnection outflows. If your magnetic field is just in equilibrium, approximate equilibrium, and it is evolving with time, even in active regions, it will evolve at the speed of photosphere. It will not. So if photosphere is moving at the speed of 1 to 2 kilometers per second, so if you have even a magnetic flux rope in an active region, it will evolve at that speed unless it gets unstable and starts to rise at 10 to 20 kilometers per second. So even at that speed, even if let's say if we consider 10 to 20 kilometers per second, that would be smaller than say a few hundred kilometers per second or thousands of kilometers per second. Yeah. So as I was mentioning that you can calculate plasma beta just from the formulation, and I thought it is important to put it out here. This is a very important paper which was put by Alan Gary in 2001. So he did some empirical modeling of magnetic field variation and thermal pressure variation with height, and gave a approximate variation of plasma beta with height. So here you will see that there are just two lines. One is on the left and another one is on the right. So in these regions, there are different parts where beta is greater than 1 and where beta is smaller than 1. So this beta less than 1 region is typically in the solar corona, but when you are closer to photosphere, because density is much higher, beta is larger than 1. And similarly in the solar wind acceleration region, you have higher temperatures. So basically beta goes greater than 1. So in the previous slide, the assumption that we were talking about J cross B equal to 0, that followed from saying that beta is much less than 1. So that condition of J cross B equal to 0 is relevant for certain regions of solar corona, not throughout the entire solar atmosphere. That is something that is important to understand. So when we are modeling the magnetic field of the solar atmosphere under this assumption of force free and 0 Lorentz force, so that assumption is valid only in the regions where beta is much less than 1, or what I'm trying to say is it is mostly applicable for solar corona, not photosphere and chromosphere. So if you want to get the magnetic field of photosphere or chromosphere, you need another model or more another equation that which is not J cross B equal to 0. So then if you have J cross B equal to 0 in the solar corona, then essentially there is, as I mentioned, there are two categories. The first category is force-free field models and relevant for solar corona. So essentially this entire equation is 0. And then if you take quasi-stationary abletion and compare all these terms, low beta in the solar corona, then you end up with a situation of J cross B equal to 0. Now this equation has three solutions. You cannot take B equal to 0, which is the trivial solution and does not have any meaning. So the one solution that satisfies this equation is J equal to 0. That is your current density is 0. And I will talk more about it. So if J equal to 0, this equation is satisfied. Another solution is J equals to alpha B, where alpha is a constant everywhere in space. So if J is alpha B, that is current density is parallel to magnetic field, then if you take B cross B, it goes to 0. So this solution also satisfies the equation. And another solution is J equals to alpha as a function of R P. So alpha is a scalar function which is not constant of space, but it can change its value. But still, this solution would be parallel to the magnetic field, and you will get zeros. So by nomenclature, we call this solution as potential, this as linear force-free field, and this as non-linear force-free field. And the second category is non-force-free model, where we are talking about photosphere, chromosphere. There we cannot use the assumption of J cross B equal to 0. We need something which takes into account this fact that J cross B is not equal to 0 in these layers of the atmosphere. But at the same time, they should also account for the fact that when we are going into the solar corona, my Lorentz force is going to 0, and therefore any model which is going to model photosphere and chromosphere, in that model, magnetic field should decay with height such that Lorentz force goes to 0 in the solar corona. So one example is again this equation. So now in this equation, we are not neglecting the first term and the third term. So just if you solve this entire equation, for example, it may happen that in photosphere or chromosphere, these terms, pressure gradient and gravitational force, are not negligible in compared to your Lorentz force term, then you need all these force term to solve your equation. So one example of this category is magnetohydrostatic model, which solves the equation J cross B equal to grad P, where thermal pressure force due to thermal pressure gradient is balanced by the Lorentz force. There are other models as well in this entire picture. There is another non-force-free model, which follows from plasma relaxation principles, but that we are not talking about in this talk. Okay, so one thing that I would want you to note here is that when we are saying J equal to 0 and still calling that there is a solution to the magnetic field, then how is it possible? Because when we say that when we have a flow of current, then only we have a magnetic field. If we do not have a current, then how do we have a magnetic field? So the underlying idea to understand behind this is that the volume in which you have magnetic field, that magnetic field is created by currents outside that volume. So inside the volume, you do have a magnetic field, but within those magnetic fields are created by currents outside that volume. Is there any question so far? So this is just this is an additional slide, I would say, because I wanted to explain more on the concept of Lorentz force, how you understand Lorentz force, what is the meaning of it, what are its components, and so on. It may look complicated. It is really not that difficult. So if you start from this first line, J is curl of B over mu naught, and then you can do a J cross B, which is this equation. And then you have to use this vector identity essentially to get your J cross B in the following form, which is 1 over mu naught gradient B square by 2 plus B dot del B. So here you will notice we are getting a term as gradient of B square, which is similar to the term gradient P which you had in momentum equation. So V square by 2 is essentially magnetic pressure, which I talked about by discussing plasma beta. So this is a force. So when we are decomposing Lorentz force, we are getting one term as gradient of V square by 2. So this is a force which is coming due to gradient in magnetic pressure. And I will talk about what is the meaning of gradient in magnetic pressure. And then there is another term which is B dot del P. This is a slightly difficult term to visualize physically or more intuitively how to think about this second term. And this can be done as follows, that the magnetic field, whatever, for example, if you have a magnetic field line going like this, so you can define your magnetic field vector as magnitude into a unit vector. So this unit vector is pointing along the direction of the magnetic field, which is represented by S hat. So then what you can do is B dot del B. So now we can write vector B as B into S hat dotted with the gradient, and then again vector B as B S hat. So now B S hat, which is in the direction of S, and this will be dotted with gradient operator. So this is going to tell you that we must take derivative along the direction of magnetic field. So then we get B d over ds, and then you have another B S hat from the vector B. So now it's just a product rule. So you get B dB over ds into S hat plus B square d by ds of the unit vector S hat. Because when you are going along the magnetic field line, the direction of your unit vector will also keep on changing, depending on where the magnetic field line is going. Yeah. So this term ds, d by ds, b dB over ds. So now this term can be written as d by ds b square by 2, because you would get a 2 outside which will cancel, and then you will get dB over ds. And then again it is the same term over here, b square d by ds of S hat. And now I'm representing this gradient as gradient of S for simplification, and then you have b square by 2. So unit vector gets absorbed into this gradient, and then you have b square d by ds over S hat. So now what you can do is how to, whenever you are faced with a question of how to differentiate the unit vector with respect to this quantity and how do you do it. So one simple way which I'm using here is that, so if you consider a circle with origin O, and you have radius vector r, and you have a point over here, let's say, which is at an angle theta. So then you have x equals to r cos theta, y equals to r sin theta. So this is your y, and this is your x. And then you can write your any vector r as, okay, it's there. R is basically xi plus yj. So you have r cos theta I plus r sin theta j. And then in these polar coordinate, you can obtain your unit vectors along the radial direction and along the angular direction. So you have r cap, which is given by derivative of r with respect to r and divided by its magnitude. So then you get cos theta I plus sin theta j. And similarly, if you get unit vector for theta cap, the unit vector along the theta direction, which is along this direction. So then you get minus sin theta I plus cos theta j. So now if you consider a element of arc length ds, which can be given by along the circle as this. So this is ds, this is d theta, and this is r. So then you note that d theta is essentially ds over r. So that your ds is equal to r d theta. And this vector, so now you have to visualize that this circle is represented by a magnetic field line. So I can equate my s cap to theta cap, and then we can evaluate ds cap over ds as d theta cap divided by dr d theta. So r is essentially your radius of the circle, which comes out, which is constant. And then you have another quantity as d theta. Okay, there is a mistake. There should not be a D before RD theta. But anyways, okay, so you will have RD theta, and then you from the formula of theta cap, you can evaluate d theta cap by d theta, which you will get as minus sin theta I cap minus cos theta I cap minus sin theta j cap. And you can take the negative sign outside, and then what you get is minus r cap into 1 by r. And the vector which is along this radius, so now we are calling it as n cap. So essentially, if you take a derivative of that unit vector with respect to length element ds, you end up with this this formula n cap into 1 by r. So now you can again write your expression for b dot del b as which is gradient b square by 2 plus b square over r into n cap. Here there would be another s which is missing, but okay. So then we have a cross b as 1 over mu naught minus gradient of b square by 2, which is coming from the gradient of the magnetic pressure plus gradient of s b square by 2, which is coming from this term, and then b square over r into n cap. So now we can decompose this term into a gradient along parallel to magnetic field and perpendicular to magnetic field. The parallel term cancels out with this term, and the perpendicular term survives, and we have another term b square by r over n cap. So this term is actually representing your tension force perpendicular to magnetic field. So as I said, you have to visualize this magnetic field line, this circle as made by a magnetic field line. And this n cap is the direction which is along the center of this circle. So what it is saying is that if you bend a magnetic field line, or in general, when you try to bend a steel iron rod, it will try to straighten itself out because you have to do work against that rod to bend it. So you are doing work to store energy into that iron beam. Similarly, for magnetic field lines, when you are bending them, it will exert a force perpendicular to itself to straighten it out because every system wants to go into a lower energy state. So if you have magnetic field lines like this, it will try to exert a force along a direction, along this direction. So what we will call this as the radius of curvature of the magnetic field. So you will get a force along this direction, which will try to straighten itself out. And this is what is tension force, which is perpendicular to the magnetic field. And the first term, magnetic pressure force, due to magnetic pressure force perpendicular to the magnetic field is that, like we have high thermal pressure region, low thermal pressure region, and the force will be exerted from high thermal pressure region to lower thermal pressure region. Similarly, we have the idea that when field lines are close together, their magnetic field strength is more, and therefore you will have more B square. But if you have a region where magnetic field strength is less, there you will have lower B square. So for example, in the case of X-type null point that we discussed, so this is the X-type null point where essentially magnetic field is 0. And these are the magnetic field lines which are going to come towards this point for reconnection. So here you have more B, here you have less B. So these field lines would be pushed towards the null point because of magnetic pressure force. They will try to move from higher region of higher magnetic to lower magnetic pressure. So that is a sense of Lorentz force, that it has two components. One is the pressure force and another is the tension force. And last thing related to that is that often in plasma physics and solar physics, you will hear terms like pinch force and hook force. So these are nothing but pinch force is essentially the tension force and hook force is nothing but the magnetic pressure force. That if you have parallel currents, they will try to attract each other. The force exerted would be such that they will attract each other. So for example, if you have a cylindrical column where you have a lot of currents parallel to each other going in, these are currents. So, and each current will have a magnetic field line around it, like this. So all these magnetic fields, what will they do is exert a tension force, And these parallel currents, because they are going to attract towards each other, so this will produce a pinching effect in the sense that this tension force is going to be exerted along this direction. So if initially the column was this big, the column would reduce to this big because of the tension force that it is trying to pinch the plasma. And this pinching effect is important when you are trying to confine the plasma in a tokamak or in any fusion device, because thermal pressure would always try to make the plasma go out of that device. So that is where pinching effect is very important. And to produce that pinching effect, often external magnetic field is used in a lab fusion plasma or tokamak to confine it, to produce that pinching effect. And second is the force due to magnetic pressure. So the idea is again of similar sort that if you have currents, if you have this circular coil is representing a current I, and then you have magnetic fields around that, because this current is going to produce a magnetic field of this kind. Yeah. You will have circular magnetic field and going like this. So now the only idea over here is that when you have currents in opposite direction, they repel each other. So here you will see you have a current going in this direction, and then you have a current going along this direction. So this represents your anti-parallel currents, and therefore they will have a repulsive force between them. And this repulsive force can be understood from the concept of magnetic pressure force, that in this region, which is within the circular loop, this area is smaller as compared to this area, and therefore the field line strength is stronger over here as compared to the area outside, and therefore your magnetic pressure is more on the inside as compared to the outside. Because magnetic pressure is more on the inside, it will try to exert a force outward, which is same as understanding the concept from repulsive force. So this force is also called as Hooke force, which is also responsible for expanding magnetic flux in the solar atmosphere. So like there are a lot of applications to understanding the concept of magnetic pressure force and tension force within the Lorentz force component. So Masaru, how much time is there?
You have 20 minutes.
Okay. So today I have kept, this is my last slide of the talk. So we have seen so far that to model the magnetic field in solar atmosphere, we need to model it because measurements are not available in the entire three-dimensional volume. So we need to model it, and to model we try to adopt certain assumptions. One of those assumptions is J cross B equal to 0, which is applicable for solar corona, but not for photosphere, chromosphere, and so on. And then we have seen how different components of Lorentz force work out. But the title of my talk was numerical modeling, and we have not done anything numerical so far. So this is a lot of numerics. So this is the example of a potential field, how to solve it. So all this stuff we need to do just to solve this point J equal to 0. We are trying to solve J equal to 0 by doing all this. And how do we do this is the following. So J equals to 0 means curl of B equal to 0, which means that you can write B as the gradient of a scalar function, which is B equals to grad phi. And then divergence of B equals to 0 tells you that del square phi is equal to 0, which is essentially Laplace equation. So for any Laplace equation, given you have the boundary condition, the solution is always unique. And I mean, this is one of the easiest equations that you can solve in mathematical physics. And then this solution that I'm showing here follows separation of variables. So we write phi as a product of three functions, capital X, capital Y, and capital Z. And then you plug in this equation, del square phi. And then you can get this equation. I think you all have probably seen it already, which is 1 over x d square x divided by dx squared, and all the terms for y and z. So we need to make this equation 0. So For the first term and the second term, we are taking it as equal to minus KL square minus KM square. And the third term is KLM square equals to KL square plus KM square. Therefore, their total sum is 0. So now if you solve these equations, for example, 1 over x, d square capital X, dx square equal to minus KL square, then KL square comes on the left hand side and then you get oscillatory solutions because you will have a negative sign on the right hand side. So then you will get oscillatory solutions of the form of sine. Similarly, for the second solution, you have minus Km square, therefore you will get oscillatory solutions of the form of sinusoidal function. But the third term, it is positive, and therefore you will get a solution which has a factor of exponential plus KLM and minus KLM along with a Z. So if you plug in all of that with the boundary conditions, then you can get a solution for phi, which is written here as ALM sin KLX sin KMY exponential minus KLMZ. So this exponential factor is coming from the Z. And this is saying that, essentially saying that my magnetic field strength is decaying with height in an exponential manner. And ALM is just a bunch of constants coupled together into this product ALM. So now, where does this thing come from that, okay, we said we have measurements from photospheric magnetic field and how do we use it? So this BZ, Z equal to 0, this term is representing a measurement of the photospheric magnetic field. So this is how we use this measurement to extrapolate the magnetic field. So this is the measurement, and because B is equal to grad phi, and therefore on Z equal to 0, this would be equal to del phi by del Z at Z equal to 0. So if you take this derivative, del phi over del Z, so you will get a factor of KLM outside along with the minus sign, and then you put Z equal to 0. So then you get BZ at Z equal to 0 as minus this quantity sin KLX and KMY. By the way, all these KL, KM and KLM are Fourier frequencies. So then what you can do is, if you put this sinusoidal product in the form of exponentials, then you can immediately realize that minus ALM KLM is nothing but fast Fourier transform of BZ Z equal to 0. So the essential part that is what we are doing here is that we are taking the photospheric magnetic field measurement, taking a Fourier transform of that measurement to compute these coefficients. Once we have all these coefficients by taking the Fourier transform of BZ at the photospheric level, then BZ is again coming from B equal to grad phi. So this is del phi by del Z. And if you take its derivative, you get minus ALM KLM sin KLX sin KMY into exponential minus KLMZ. But I know that I can replace my Fourier coefficient from the fast Fourier transform of BZ Z equal to 0. And again, converting this sinusoidal in the form of exponentials, you can write it as fast Fourier inverse of the entire quantity, because ALM KLM is now replaced by the fast Fourier transform, and then sinusoidal, the product of these two sinusoidal gets absorbed into the fast Fourier inverse fast Fourier transform, so that you can obtain BZ. Similarly, you can take derivative with respect to x and with respect to y, and you can write it as FFT inverse of this quantity. Because if you put sinusoidal in terms of exponentials and you take a derivative with respect to x, you will get a factor of IKL outside. And similarly for the y component, you will get a factor of IKM outside. And so this is how you can get Bx, By, and Bz in the entire three-dimensional domain, where you are using just photospheric magnetic field measurements. Now, I did not want to leave it just like here, so I am showing you a numerical code which is doing a potential field extrapolation, and this is the result of that extrapolation. So this is very quickly what so here we are taking three data components. BR data is essentially BZ component on the photosphere. BP and BT are BX and BY components on the photosphere. Now it turns out in potential extrapolation, you do not need these two components. Only the Z component is enough for potential field. And this is creating the Fourier frequency. So KLA and KLB, this is end-gen is index generator. So if my photospheric magnetogram, it is coming out in pixel units. along the x direction, it has, let's say, 100 pixels, and along the y direction, it has 100 pixels. So nx has 100 pixels and ny also has 100 pixels. So along the positive x, we are constructing an index generator as half of that, and along the negative direction, we are constructing half of the frequencies. So then we combine KLA and KLB to get a frequency spectrum along the x direction, and on the y direction to get a frequency spectrum. So then this is just multiplying in the form of Fourier by 2 pi divided by nx and 2 pi divided by ni, which you essentially do whenever you have a Fourier series. 2 pi by length scale and 2 pi by length scale multiplied by whatever the integer number is, so that you get all the frequency components. This part is, I would skip. This part is not much relevant in terms of, this is just replicating the entire Fourier component along the x and y direction, so that you have a two-dimensional distribution of all the frequency components. So then you get KLM as, because we described here as KLM square as KL square plus KM square. So here you have KLM as the square root of KL square plus KM square. This BLM is fast Fourier transform of the photospheric magnetic field measurement, which is represented, which is you can see from this equation. And then ALM is BLM divided by KLM, which again you can see from this equation, that you can divide KLM and get ALM. Now these argument of x and arg y are these components that which is shown here, which is ALM AL into I. So this imaginary IM is just a complex number I, and then you get one for the y component as over here minus ALM into IM into KM. So IM is the complex iota, and then you define these three arrays Bx, By, Bz, and then you're running a for loop. So we are just doing the fast Fourier transform, which are shown here. So for the x component, you have argument of x, which is ALM KL into I into exponential minus KLM into K is representing the z direction. And then similarly, you can get Bx, By, and Bz component. So this is showing you an example where we have taken a magnetogram and run this code to get a potential field extrapolation. So you can see there are like different magnetic loops that are connecting positive to negative polarity. Another thing you can see, this yellow field line I have drawn to show you a QSL, that at this end of the field line, those field lines are closely spaced, but when you are going out, these field lines are spreading out. So this is the essential structure of a QSL that I was talking about in the previous. So I think with that, I will stop and take any questions.
Is this MATLAB code?
This is a code in ideal.
Oh, ideal. Okay.
Yes, but I suppose it would be straightforward nowadays, especially to convert it into Python or MATLAB or anything else. Really, yes.
Said at the beginning that you use a force-free approach for the particular corona,
Yes.
and non-force-free approach for the photosphere and chromosphere. How do you know that? I mean, is there a factor of observation or?
How do we know that we have to use non-force-free?
Yeah.
Yeah. So as I mentioned, with one of the evidence for that, in support of that, is this plot, which is plasma beta. So you will see that close to photosphere beta is more than 1. So when you compare, when you put this beta larger than 1 along with the pressure gradient term, then you know that this forcing term is not insignificant or negligible compared to the Lorentz force. Also, when you are going to chromosphere, there we have neutral. So the dominance of magnetic pressure force comes from how much conducting or how much ionized the plasma medium is. In photosphere, the temperature is less, but density is much larger. Therefore, plasma beta tends to be larger than 1. So basically, on the basis of beta and other characteristic parameters of the system, we compare it with the Lorentz force and then see. Then we know that, okay, this approximation is not valid for photosphere and chromosphere.
Thank you.
Talking about boundary conditions, I mean, whenever you're solving that field like this, you just given the, for example, in your research, where do you get your boundary conditions?
So when you are looking at for example, in this particular potential extrapolation, for example, because you are using Fourier component, so along the x and y directions, we put periodic boundary condition because we are using Fourier series. Then, so x and y directions are resolved with periodic boundary condition. For z equal to 0, the magnetogram itself is the boundary condition because that is what we are providing as the boundary on the bottom layer. And then for the top layer of Z, the assumption is that your magnetic field strength goes to 0 as you are going higher in the atmosphere. So in the top layer, the magnetic field is 0. So that is how we construct boundary conditions. For example, in this extrapolation and for most of the extrapolation.
And do you always use the Fourier investment source, or do you use other methods for different kind of?
But mostly for all the extrapolation that I talked about, whether it is potential, linear, nonlinear, force free. Not nonlinear, force free also you use potential as a part. So most of the non-force free code that I have worked with 4-5 code. All of them we use Fourier expansion to solve these equations. And for Laplace equation, you can